Alright, so like I said, we are going to work through the problem on page 598. So grab your book out, be looking at this. Don't just come to class, spend some time on this, please. The more comfortable you are with it when you get to class, the more we can work through different things, the better off you're going to be. So please don't just watch this and say, I don't get any of it. Watch it a couple times, work through it, get as many questions as you can about how to do this, so that we aren't just shooting into a barrel hoping to hit some fish. We're actually, laser pointing them when you get here. But, okay, so 598. Assuming that the reaction of the formation of gaseous hydrogen fluoride from hydrogen and fluorine has an equilibrium constant of 1.15 times 10 to the 2 at a certain temperature in a particular experiment, 3 moles of each component was added to a 1.5 liter flask. Calculate the equilibrium concentration for all species. Okay, so what we have to do first is figure out what is the actual concentration of everything, and concentration is amount of stuff per volume. Well, in this one it's really easy. They say that we have 3.000 moles of my H, my F, and my HF. We're starting with all of them. And we put that into a 1.5 liter flask, right? So my concentration for everything here is 2 molar. All right. So then I put this into my equation to get Q, which is the same thing as K, but this isn't to solve for, it's to see what my equilibrium is at this point. If it matches my K, then this is a really easy example. Of course it won't, because then it's worthless. But so we're going to go my products, which is my HF2, right? If you look up at the formula, the coefficient is 2. H2, F2, I have 2 molar, oops, one more 0, and 2 molar. Okay, everything, we said that everything had that concentration because we started out with 3 moles of everything in the same volume. So that's 4 over 4. So Q is equal to 1. Well, my problem says that my K is equal to 1.15 times 10 to the second. So these things do not equal each other. So I know that I have to shift, that I have to either gain products or I have to lose reactants. Or I have to gain reactants. I said the same thing there. Gain products or lose reactants. Well, that's one way for it to go. Okay, so how do I know? Well, that goes back to what we said about the Q before. If my Q, which is less than my K, which in this case it is, 1 is much less than 115, okay, then the system must shift to the right. Okay, so I'm going to consume this, I'm going to lose this, I'm going to gain that. Okay, so that's what Q is going to be telling me. So I know what way to draw my X's and O's and everything in there. Now, this is where that ice thing comes in. All right, I know ice, CE. I know my initial concentration, and I do this for every separate species in the flask. So I know that my initial concentration of hydrogen is 2 molar. I know that I am going to, since I'm shifting to the right, I'm going to be using up that concentration. So I'm going to minus an X from that. I don't know how much of it I'm going to be using up. That's what the problem is going to be telling me, is how much. What is that change going to be? Okay, I just know that I'm going to use it. So my equilibrium will be 2 minus X. Okay, this is going to be the same for my H and my F. they're going to have the exact same thing. My HF, on the other hand, initially I'm going to have 2.000 because everything had that. We calculated that. So that's my initial concentration is going to be that, right? I am going to change it by X now. I'm going to add X because I'm making more product here. Okay, so instead of subtracting it, since my reactants I'm getting less of, I'm going to subtract X from it. My products I'm going to be making X, so I'm going to add it. But it is going to be added at a rate of 2 times what the others were lost at. Right, so using that coefficient again. So this is going to be 2X instead of just X. Okay, and so my equilibrium constant then is going to be 2.000 plus 2x. Now I'm going to take my e's and I'm going to put them back into my equilibrium. So K is equal to my HF squared over H2 F2. I'm going to exchange these concentrations for what I found for my concentration. So I'm going to get rid of this because I don't know what that is, and I'm going to say my HF 2.000 plus 2x squared. Okay, what I found back here, this I'm going to plug in, okay, because this was my HF. Okay, I'm going to plug that in to here. And then my H2 and my F2 we found is this one. So I'm going to plug those in to my equation. So I'm going to go all right. So now we're gonna, and then it said at the start that my K is 1.15 times 10 to the 2 equals this now. And so now we solve for X. All right. And the book goes through like all the different steps like that. If we need to, we can do the math part when you get here. But X turns out to be 1.528. Okay, so now we go back in. I know it keeps going on and on and on. But now we go back in and we said that H, the concentration of H squared, was equal to 2.000 minus X. We now know that this is this number. So the concentration of H2 at equilibrium, not at the start. This is what it was at the start. When everything's all said and done, I am going to have 0.472 molar concentration of H2 and of F2 because they happen to be the same in this problem. All right. Then my HF at the start was 2 molar, but we changed that. We said 2 molar plus 2x. We now know that x is that 1.528, so we can put that in there, and we find out at the end that HF, the concentration when I reach equilibrium of HF is 5.056 molar. Okay, so incredibly useful tool. You're jumping all over the place with what we're doing. We've got to do like 7 different steps to get this all done. We'll work through these problems and we'll make it as easy as we possibly can for you. Hopefully, between these 2 videos, everything works out, and we will see you guys in class.